right, welcome back, everyone. So we're fortunate to have with us today Zaid Harchaoui, who is a professor in statistics and computer science at the University of Washington. Has done a lot of really nice work on learning under distribution shifts recently, and is going to be talking to us a little bit today about learning from different modalities and sources. So quite relevant to the workshop topics. All right, thanks.
Thank you. Thank you, Ginger. So I want to talk about the new learning paradigm that has now pervaded in our practice of machine learning. We have some data generating distribution P and some evaluation distribution Q, which may or may not be the same as P. And we're learning something from P, and then we're trying to evaluate it on Q. And most recently, we're not doing that with just like a simple machine learning method, but we're training something that seems to be somewhat more ambitious than a simple machine learning model for a particular task. And that's what we call a foundation model. And then we use, in many situations, something called a prompt, which has many meanings and many denominations. And we use that, and we can turn this foundation model to generalize to unseen tasks, so tasks that were not in the training of the foundation model, and sometimes without additional training data. Okay, so this is the main topic of this talk, and I'll try to share with you some insights we've found about this learning paradigm. Okay, so there are many instances of this, like from GPT, but also Dino and contrastive learning framework and so on. Okay, so let's be more precise about this. So in classical supervised learning, we have some input data X, and we pass it through some image encoder, which may be pre-trained, maybe trained as well for that task. And then we predict. And what do we predict? We predict labels that are very clearly defined. So here we have 4 labels that correspond to some class categories of images: moon, sun, star, planet. And then at prediction time, we just take the highest score and we predict that label. And that's the textbook machine learning 101 that we're all familiar with. And nowadays, instead, we take those large foundation models and we train them most often using federated learning from large amounts of data that are heterogeneous and come from many sources and include many classes. And then with that, we are able to predict on those classes, but also other ones. And the capabilities that emerge from those models seem to be like really impressive. And that fuels like this sense of like the emergence of like a more general intelligence than the one that was encompassed by supervised learning. Okay, so what is foundation modeling? And that's the main goal of this talk, is to try to frame this in a very basic, elementary terms, in the same way we understand well supervised learning. So in foundation modeling, the one that I consider here, we have input data X, and for simplicity, we're going to assume it comes from one modality, that is images, right? So visual domain. So we have some X, and say it's an image of a sun, and we pass it through some image encoder, we get some vector representation of that image. And then we have some other modality. So here, for simplicity, I'm going to assume it's text, so it's natural language. And we pass it through some text encoder, and we have also another image representation. And in pre-training, in many of those foundation models, there is no specific task that is specified during the pre-training phase. So we call this task agnostic, right? So there's no specific image classification task or image retrieval task or image segmentation task, or there's none of those. And yet at evaluation time, we may have some task at hand, but we well, we don't have a specific supervised learning pipeline to predict some labels. Instead, in computer vision nowadays, what people do is they write prompts, so they type prompts that are in natural language that correspond to descriptions of the concept they're trying to capture, right? And so prompts is a little bit confusing here. I think the more rigorous term would be a pseudo-caption. So they write many of them, and if you look at codes of those pipelines on GitHub, you will see that to reproduce results, people provide a file that lists all the pseudo-captions that correspond to specific classes, right? So like you have 100 of them, or 50 of them, or 500 of them, right? And you have all those variations on the same theme of the particular task, and then we pass this through some text encoder. We get many representations, and then in order to predict, we can predict in absence of any data whatsoever for the task downstream, right? And I'm emphasizing this because, of course we could do fine-tuning, we could do few shots and so on, but just like what is really impressive is that even if there is zero data on the downstream task, we can still do something really impressive. So we, in order to predict on a particular task that somewhat relates to those pseudo-captions or prompts, we simply take the highest inner product between those vector representations. And so this decision rule seems like really primitive, right? It seems to go back to like the early days of machine learning and pattern recognition, right? It's just like nearest neighbor, right? And yet this achieves performance that is on par or sometimes superior to machine learning methods that were trained end-to-end for the specific task at hand. And so this is really puzzling. And so the foundation models that I'm referring to here are like CLIP. So CLIP is a contrastive model that was trained on pairs of text and images. But also Dino. Dino is a foundation model from Meta that now achieves like state-of-the-art performance across all classical, well-defined computer vision tasks. And so I'll show here like an image of the performance that is achieved by Dino. So they take like semantic segmentation, image retrieval, image classification, and so forth and so on, and they evaluate in terms of accuracy on those specific tasks. And the performance they achieve is like state of the art or superior, or setting a new state of the art on those tasks. What is the classical approach? The classical approach would be to train a computer vision pipeline for the specific purpose of semantic segmentation, or to train a computer vision pipeline for the specific purpose of image classification, like ImageNet and so on. But here, we just trained this gigantic model that was on data that was downloaded from the web, so common crawl, and then we train that in an unsupervised manner. And then yet we can achieve a superior performance. So the question is like, why? What is going on here? Okay, and so people at least in the report associated with this Dino paper, they refer to this as like preparing gourmet meals, right? So they like specific recipes in data processing and model training that allow them to achieve this good performance. Okay, and so what we want to understand here is like this from the viewpoint of statistical learning theory. So what is exactly happening in terms of generalization, right? So what is happening? How does this generalization relate to the usual definition of generalization we are used to, and that relates to some extent to Samori's talk that we just had. Okay, so what I show is that a core concept that underlies many of those pipelines is this basic object from statistics and probability, which is the Radon-Nikodym derivative, but that's not the Radon-Nikodym derivative between two marginal probability distributions, but it is instead, you take the, say X is the image data, and say Z is the text data. And so PXZ is the joint distribution between the image data and the text data. And then you're going to consider the derivative between the joint distribution between the two modalities and the product of the two marginal distributions on each of the probabilities, right? So that's one way to write it. And we shall see that this derivative, this score that shows how different is the joint distribution from the product of the marginals. This score, we shall see that it's a measure of dependence between x and z, right? Another way to write it is to condition on one modality, so say x, and then write the derivative between that conditional divided by the marginal over z, right? Okay, so this derivative relates to a measure of dependence between x and z that is known as the mean squared contingency, although here I do not write it in the classical way. There may be a log term, it depends on what papers in information theory, but it basically captures dependence, right? Another way to write it, and is inspired by tools we have for producing kernel Hilbert space, is to look at conditional expectations of nonlinear functionals of z, right? So say you condition on x, and then you take any, say, measurable function of z, right? You can take it in an RKHS, you can take it in L2, and you compute the expectation of g of z given x, right? So we're going to have this operator, which we call the conditional mean, which gives us the conditional expectation in a nonlinear way from z to x, right? So those are two notions that we shall see that they are somewhat dual to each other and capture many ideas in this literature. Okay, so I want to just do a digression on the origin of this idea of zero-shot prediction before we dive into the mathematical ideas. So I want to pay tribute to this groundbreaking paper that appeared in the late 2010s on matching words and pictures, and it echoed a paper that was co-authored by Mike Jordan, among others, on matching words and pictures, and Nando de Freitas. And that's the origin of this zero-shot prediction. Another origin is meta-learning. But the real paper that created the setup that we're referring to in this talk is this paper by Hugo Larochelle, Dumitru Eran, and Yoshua Bengio, and that was like in 2008. And so this idea of zero-shot prediction is like familiar in computer vision, but one thing that is interesting is like for a long while, it just didn't work. And there were many papers on this, including from my group. And so back then, so say 10 years ago, what we would do is we'd take images and compute features of images, and we take attributes that are like short text that describe the object of interest. So say like a whale has a tail, a whale is a big fish, or whatever. And then we would compute some dependence measure between the two domains. And back then, what we were trying to show is that if we do that and we add some data points for the task, downstream task, if we have, say, 10 of them or 50 of them, we would achieve similar performance as something that was trained end-to-end for that task specifically, right? We wouldn't have expected that when training this in an unsupervised manner, we would achieve state-of-the-art performance as CLIP did across all tasks in computer vision. So that's really what happened here. Okay, so how do we interpret this from a learning theory viewpoint? Okay, so first of all, like we want to define the various distributions that are at hand here, and then define the population version of all the quantities we want. And that's not as easy as it may sound. If you look at papers on zero-shot prediction, it's like things are described in a procedural way. So like they're not described in ways that are aligned with learning theory. And then we'll provide risk bounds, which are preliminary, so they're not like as tight as like the state-of-the-art statistical learning theory bound, like say supervised learning, but I think they lay the groundwork for developing more refined ones. Okay, so you have data, say from image domain and text domain, right? And you can describe the data from the internet, say the whole internet, as PXZ, and that's the pre-training distribution. And then you have some evaluation distribution. And the evaluation distribution has, say, images, and it has labels. But those labels are not the same as the text, information that you had in the pre-training stage, right? So the labels are Ys, and at the pre-training stage you had Zs, right? So those are like pseudo captions or just like commentaries on the images, right? And even if Y was equal to Z exactly, right? There is no reason for P to be equal to Q, right? So those are fundamentally different objects living in different spaces, right? Okay, and so if we have some predictor eta, right? And we look at the best predictor if we knew the distribution at the evaluation stage, if we had an infinite amount of data at the evaluation stage, which we never have, then we could describe the best predictor in population with this equation, right? And here I'm using least squares because later it will help us perform a decomposition of the risk into meaningful terms. Okay, and so this eta, right? So this is the regression function in learning theory. This is just the conditional expectation under QXY, like under the data that we don't have for the downstream task, and it's if we have an infinite amount of them, that's that conditional expectation. But what zero-shot does is not that at all. It is basically nesting two conditional expectations. It is nesting a conditional expectation under the pre-training data, right, which is gigantic usually, it's very large, and another conditional expectation which is under this prompting mechanism that we use to define the labels, right? And by nesting those two conditional expectations, we obtain the zero-shot predictor. So that's what would happen if we could use an infinite number of prompts and an infinite number of pre-training data points. Okay. And so the question is, how those two regressors compare? Even if we have infinite amount of data, there is no reason for them to be equal, right? So there is no reason for the zero-shot predictor to do as well as the predictor we would have had if we had an infinite amount of data for the downstream task, right? So now, if we have samples, it's even worse, okay? And so what's going to drive the performance is the compatibility between QXY, PXZ, and RYZ, right? Those three distributions are driving the performance, okay? Okay, so there are two main approaches. So one approach is to look at nonlinear condition expectations between X and Z, right? Between X and the image data and say, some functional of the text, right? And we capture this with this conditional mean operator. And that we call the conditional mean viewpoint. Another approach is to use information density, which is to compare the joint distribution to the product of the marginals. And we'll see that they are somewhat related. So let's start from the middle. So consider a nonlinear covariance between X and Z, right? So you take some function H on the X domain and some function G in the Z domain, and then you're computing the expectation of those two nonlinear functions and X and Z, right? So this is a way to measure any covariance between any function, any encoder, say, of the data, right? So you can relate this to the conditional mean operators by conditioning on X. Now you have this nonlinear conditional expectation. Then you multiply it by h of X, and then you get this compact representation of this function, which is the projection of the conditional mean operator evaluated on G onto the direction H, right? Under the marginal distribution P of X. If you do the same process on the other side, you will get the projection of the conditional mean operator from x to z, evaluated on h, projected onto the direction g, right? Under the distribution, under L2 of Pz. Okay? So because of this symmetry between the two modalities, what's going to happen is that you can jointly diagonalize those operators, right? So you can jointly diagonalize them onto the same, and they will share the same singular values, right? So you will get a basis of L2px, that will be alpha 1 to infinity, and a basis of L2pz, that will be beta 1 to infinity, and then you can expand those conditional mean operators onto those singular vectors. And what's beautiful here is that the singular values capture the dependence between x and z, right? So if the first singular value has no use, right, it will always be 1. So you can throw it away. And then the next singular values, the one from 2 to infinity, they capture the dependence between x and z. So the larger they are, like the slower the decay, then the greater the dependence between x and z. So here x and z are like image and pseudo captions. Right? And then if you take the L2 norm of the spectrum, then you get a well-known measure of dependence that is called the mean square contingency in information theory and kernel-based methods. Okay, so if it decays very quickly, right, if there is no mass beyond S1, then it means that your pairs, they just have no connection. There's nothing to learn from all those pairs between images and text. If you have large mass, if it's decaying slowly, then it means that there's something to capture there. Okay, and so turns out like you can if you take the Radon-Nicolin derivative and you do you subtract 1, so you subtract the part that is supported on the first singular value, so you get like everything from the second one onto infinity, then you can recover the mean square contingency. Okay, so now I want to describe two approaches. So let's describe the blue panel, so the one on the right. And this is exactly what CLIP does and other like VCREG and many other approaches do. So you can think of like the first stage, the pre-training stage, as learning something that scores similarly to the Radon-Nicolin derivative between the joint distribution and the product of the marginal, right? So they're learning something that captures the dependence between image and text, right? And if you call this R of xz, right? If you have something that is calibrated to score with that Radon-Nicolin derivative, then you can take that score, plug it in your conditional expectation formula, and then get the form as zero-shot predictor, right? In population here, right? So you take this R xz, and then you multiply it by y. Now that you have like the some labels, and then you can get your zero-shot predictor, and then you will pay a price which will be the distance between Pz and Rz, right? So the images on your downstream task and the images you had in the pre-training stage. Okay. The other approach you could do, which is actually more consistent with like what you would do in supervised learning, but I'm not aware of any large-scale system that actually operationalize that, is a conditional mean approach. So the first stage you say like, I want to go from x to z through. I want to get from x to y through z, right? So you first learn a predictor to go from x to z, right, using some supervised learning, some big neural network. And then you learn another predictor that relates a y to z, right? And then by composing those two predictors, you can go from x to y. Okay, let me unfold this. So basically, like if you take this conditional mean approach, what's going to happen is that if you take the zero-shot predictor in population and you compare it to the supervised learning predictor, the one that is new beforehand, the data and the downstream task, so this is like regardless of any amount of data. This is like for infinite data, right? You can upper bound this by the mutual information between x, y, conditionally on z, right? So the images and the labels conditionally on the labels you had, on the captions you had at the pre-training stage, plus the difference between the prompt distribution. So this is the distribution of the labels given the images. And so this is like GR and GQ, which is the same thing evaluated on the evaluation distribution. So the only difference between those two formulas is that you take the conditional expectation with respect to a different distribution. So this is the evaluation distribution, and this is the distribution you use when you actually perform this prompting. Okay, and so now if you replace all this with samples, you will see that you will have two non-parametric rates. One that will relate to the pre-training stage, that will learn this non-parametric mapping between x and z. And that's the first term. And so you have a classical non-parametric rate, although it's not tight, what I'm presenting here, but we can discuss this offline. And then the second rate, which relates to the prompting mechanism, which in this case also estimate a conditional expectation, and you will pay another parametric rate where m is the number of prompts. Okay, so now the information density approach is actually more, I find more interesting. So in the information density approach, the sum of the two rates is different. So the first rate, the pre-training stage, will be like a non-parametric rate because you're estimating this big model that approximates the Radon-Nikodym derivative. But the rate you have in the prompting stage is a fast rate per learning standards. It's 1/m, right? So basically, you put all the difficulty of the problem into estimating the Radon-Nikodym derivative, and you make the process very easy downstream, because now all you have to do is estimate an empirical average, right? And this seems to be like a theoretical explanation of why this process is actually very convenient for users, because people just download this foundation model from say Hugging Face, and all they have to do is like generate like 100 of prompts of pseudo captions to describe the image, and that's enough to get a good predictor. Okay, so another way to show this is basically you have these two conditional expectations that allow you to build your predictor, and you inserting the similarity score to perform your prompting, and the similarity score is the Radon-Nikodym derivative. And you have two complexities, one that is a regular sample complexity for learning the foundation model, and another one that is the prompt complexity. And so what's really fascinating here is that in this information density approach, or like similarity score learning approach, it treats the dependence between x, y, and z in a way that is not really the way we would use for if we were to model this dependence using a probabilistic graphical model, right? So in a probabilistic graphical model, we would say you have images and you have pseudo captions and you have the labels, and we would draw edges which may be directed or indirected, and we would try to use Bayes' rule to go from to follow a path. Here in this similarity score learning approach, what you do is you capturing the relationship between x and z with something that is the Radon-Nikodym derivative, which you can use both ways, to go from z to x and x to z, and that's why I'm not using an edge here. And then you're using a trick, which is this composition rule here, and that's exactly the tower property, by the way, for conditional expectations to go to y. In the conditional mean approach, which hasn't been operationalized as far as I know, you're just composing something, and you're basically looking at this as like, I have images, and that's x, and I have y's. I will have y's downstream, right? And I'd like to, if I were to do supervised learning for the downstream tasks, so if I would follow, if I had like samples from the downstream task, I would just do that end to end, then I would learn an edge from x to y, right? But I'm not doing that. I'm taking a detour, right? So foundation models are taking a detour. So they're taking a Z. That is like some course data that you can download from the web. And then they're learning, you would learn a predictor from X to Z and then a predictor from Z to Y. And if you, by taking this detour, you would take an indirect path to prediction compared to the classical one of prediction. Okay, so so another way, so we have the full bound here, and which describes like how the error decomposes into like the predictor you would have if you had infinite amount of data for the downstream task. So that's the direct predictor, right? The ZSP procedure is the estimate you have just from samples from the pre-training stage and just those prompts at the evaluation stage. And you see that there's somewhat an incompressible error that derives from like this, taking this indirect path to prediction, plus another error that is a learning error. And we've seen before that, you know, it has like this rate that decomposes into terms that correspond to the two stages. Okay, so in practice, what you will see is that if you look at like some experiments on classical image benchmarks, you can compare different types of prompting that capture this prompting distribution, and you will see that if you condition the prompting to the class, so it means like if you write a text where the text that unfolds is conditioned on the fact that this is all about that specific task. So say like so like an unconditional prompting would be like, say, a photo of a cat, an image that includes a cat, and blah, 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 blah. A conditional prompting would be one that where you would say a cat is like sleeping on a sofa and the cat is like making whatever now, this kind of sound and so on. So it's like very specific to that particular class, right? So then you achieve a faster rate, right? So the accuracy grows much faster, right? And this is also captured by our theory. Okay, so yes,
Sorry.
yes.
I'm trying to map this back to the results you just showed on the previous slide.
Yes.
There were two terms. There was the prompt complexity and the prompt bias.
Yes. Yes.
How are those showing up in the experiments that you just?
So basically the prompt complexity that I did not. So the prompt. So in this term, there is a term called the prompt complexity, and that relates to Rxy. And Rxy is better captured if you use the conditional distribution of y given x, right? And that's what we see here when I talk about the conditional prompting. The yellow curve corresponding to leveraging the fact that you have y given x. And the other one, the one that is unconditional, you're just using pairs of xy, and you're not conditioning the prompting to the specific class. Yes. And so in LLM literature, this conditional prompting, I think they call it QPL. Yeah, QPL is a popular prompting tool, and in fact, like if you look at Hugging Face repositories or GitHub repositories, you will see that people basically transmit prompting for this class or that class that work well with this foundation model or another. And the best class of prompt, the best type of prompt are class conditional. All right. So I'll end here. So I think foundation models like open like new possibilities, and some people question or discuss like a general type of intelligence. But I think in a more sober way, it is basically using composition rules on prediction, right? Composition rules on conditional expectations in order to expand the generalization abilities of foundation models. And it's a much more down-to-earth formula and that is captured in one single equation that actually drives this generalization more than something mystical. So this is joint work with great students and a great collaborator, Ronak Mehta, Lang Liu, and Shumik Pal. And it appeared at ICML last year, this summer actually. And yeah, and there are many more details in the paper that I didn't have time to cover. And thank you for your attention.
Questions for Zaid? I guess one question I have here is, what are you interested in looking at moving forward in terms of the analysis here? I'm curious about, ways you think you could extend this.
Right. So originally we wanted to go all the way, like we have a bound that has like the information theoretic error, the learning error, but also the optimization error, right? In relation to federated learning and so on. And so one thing that is difficult, at least for us, is like how to capture the fact that the pre-training distribution is heterogeneous, and what is exactly the right framework to model that, and then reflect that in the optimization guarantee. Right? And so, of course, like the one approach is to say it's a mixture, and and this and that. But for text, we know that it's not. I mean, at least to me, it's not very. I'm not convinced by the mixture framework. For instance, if we say there is high quality text, like from like literature, and there is poor text from Reddit, is the mixture really like how do we capture the fact that it's better quality text than others? I am not sure. So I'm still we're still thinking about that, but that's the next step, is to capture the fact that the pre-training distribution has different components, and each one of them contributes differently to the prediction downstream, and then factor in the optimization error. But yeah. So. Yes.
I didn't quite follow what M is. What are the type of examples?
So let me go back to if you forgive me, I'll go to the beginning. So M is how many ways how many sentences you use to describe the concept that you're trying to capture at prediction time. So you have this foundation model, you go to Hugging Face, download the foundation model, and then if it's a contrastive or self-supervised one, then and now you want like a classifier or a retrieval system for, say, something that is like a microchip. Like, right, you want something that recognizes a specific type of microchip. It's very unlikely that that kind of images occurred in your training stage, right? So you say an image of a microchip. A microchip image in which we can see like the different circuits and da. So that's the conditional prompt and so forth and so on. So you type that and you write like a list of them, and you write like tens of them, right? So say like 50, 100, right? And then you feed that, you pass that to your text encoder, right? And just by doing this cosine similarity or like nearest neighbor rule, you will get a very good classifier of that type of image. Like, it's quite surprising. And so M is the number, is 50 or 100. It's the number of ways you have used to describe that particular class. And so the fact that with just 50 of them or 100 of them, it's sufficient to get like high accuracy, it's basically like, it's a normalized way to say you have a fast rate, right? And so it converges very quickly. Sometimes you just need 10 of them. So, yeah.
I'll ask you more.
Yeah, of course, yeah.
Great. Let's thank our speaker again. We'll be back at 1:30 for the next session. So we have a break for lunch right now.